So the main difference is that now you know what the correct distance is. Okay.
For each injector.
Exactly. So you don't need to do it for every injector. Okay. You just need to do it for one. Okay.
Oh, okay.
So let's check one injector where you have lots of data. One injector that behaves really well.
I think this one with the red one.
So what?
This one, crockery 3.
3 microseconds,
Yeah.
110
Yeah.
nanojoule. Okay.
Around some 36.
Let's go to that one. So, and what is that? It's run 36. So,
I think it's need to be up.
yeah, I can see that. So we go to 3 microseconds and 110 nanojoule.
And run
Okay. And run 36. Okay. And so in here, you should have opt param. Okay. Again,
Yeah.
you only need to do this for one injector where you have good data. Okay. And so you see here, you have all the different opt values. Okay. So, and basically what you want to do now is to remove the geom files. Okay.
all the geom file.
These ones. Okay, because these ones are old geometry files. They're not for your system.
Oh, okay.
Okay. And so now you do know what your geometry file should be, isn't it? So what's your geometry file for this one?
Oh, I just copy this one. Okay.
Ah, this is the one that you
Yeah,
had.
yeah,
Okay,
okay.
sorry
That's
about
fine,
that.
that's fine.
So that means that we go to
Go to
what is it?
Dist opt.
Dist opt. Okay.
and course 0.0922 22
922
and yeah and
slash
p and yeah and zero the pre
yeah. So
yeah, that's one.
bread refine, and we copy it here. Okay, good.
Yeah.
So it's this one.
Yeah.
Okay, and now if we go from, so each of these optimizations corresponds to one run of optimization. Okay, so if we look at the first one, okay, opt sh, okay, this one. So what this is the content of the file. Okay, and so what is this telling us? So what this is giving us is the different parameters up here. Okay, see, we have tolerance 10 10 10 2 2 2, threshold 2800, min pix count optimized 2, log background count optimized 4, min SNR optimized 4, rad opt, let me see, and what is it exactly? And it's trying to optimize the threshold. And what's the threshold optimization? Let me see. Oh yeah, see, thresh minus thresh plus is here. And is it going to do it like that?
So what is this optimized for?
Exactly. Let me just check that everything is running as it should. So threshold is here. So okay, what we want to optimize here, okay, all of these parameters are the optimizations that you want to do for analyzing or for optimizing the way that the system should try and find peaks and then integrate those peaks. Okay, so you can go into the Crispell manual to check them in more detail, but I can give you an idea of what each of these do. Okay, so tolerance, okay, is the reciprocal space maximum variance from your geometry that the system will accept. So that means that 10 means 10% over whatever your system, whatever the unit cell is that you provided. Okay? So 10% A. So you can see it has a total A, B, C, alpha, beta, gamma. Okay.
Yeah.
So A, B, and C is in percentage. So if we tell a tolerance of 10, that means that whatever value you gave it with A, it's that value plus minus 10% of that value. Okay. Alpha, beta, gamma is in degrees.
Oh,
So it's plus minus 2 degrees. Okay, good. So they're a bit larger than normal. The normal values. So Crispell takes 5% and 1 degree, and I made it twice as big because, as you know, we sometimes have double peaks, and so I want to keep everything in place. Okay. Then later we can clean it up. So now the tolerance, I wouldn't modify it. You You can keep it as it is, okay? Now the threshold is that, so the threshold, the idea is you have your detector, okay? And the detector, of course, has a certain amount of noise, okay? So what does these values, most of these values actually have a physical value but it's defined by the detector itself. So I can't remember in many of the cases what is the actual physical value or what do they correspond with. If I remember correctly, it corresponds to electron counts, not to photon counts, okay? So basically, how does the detector work? Well, the detector has a pixel. What is a pixel? Well, a pixel is simply a photoelectric cell, isn't it? That where when a photon hits the cell, you get an electrical current, isn't it? And behind it, you have a voltmeter that measures what is the difference in potential over time, or what is the current over time, and thus it counts electrons. And when it counts electrons, it tells you how many photons have fallen on that pixel, isn't it? Now, of course, between that you have several circuits, including an amplifier, isn't it? Like like if you like music, you know, music. Like if you have some kind of player, in between the player and the loudspeakers, you have an amplifier that will magnify the signal of whatever you're playing, isn't it? Pixels also have that to magnify the signal and then be able to collect it a bit, to measure it a bit more easily, okay? But whatever, it has all these different things, okay? And of course, given that, it also has some noise in it, isn't it? The noise being the result of an electrical current passing through the detector, so through the pixel detector, without an actual photon hitting the detector, isn't it? Good. So that means that's the reason when you look at an image of what's called coming from the X-ray, it looks like grainy, doesn't it? It doesn't look completely flat. The background is not like when you take a picture and the background looks like you take a picture of a white wall with no features. It looks white and smooth, isn't it? So, however, for such a fast detector as this one, the background doesn't look so smooth at all. Okay? What it looks is there's quite a lot of noise there, and so that's why you see this kind of grain back there. So some pixels are black, some pixels are white, some pixels are different values, because they have, over the data collection time, they have some electrons coming through, isn't it? So that means that now one of the big things, or one of several of these variables, are going to be how do we define a pixel compared to that background noise? Or sorry, how do we define a peak compared to that background noise? Okay? So the threshold is the minimum number of counts that the detector at the pixel level has to do before it defines that pixel as containing a peak. So, meaning, for example, 200 may mean that at least 200 electrons have to go through. Okay? 2000 means that at least 2000 electrons have to go through. You see what I mean? Okay. So, then the next thing is min-pix count. So min-pix count is what is the area, okay, the minimum area that you will define as a peak. Meaning, let's imagine that you all of a sudden have a big spike in noise, of positive noise, meaning lots of electrons passing through something, but only on a single pixel. That is possible, isn't it? But if that's the case, if that is noise, you would not expect the same thing to happen on all neighboring pixels. You see? Because that's a stochastic effect, isn't it? It's a random effect that only happens on one pixel. So it's difficult to imagine that it would happen on that pixel and say on all, if we say one, and each pixel around it. So this pixel and 1, 2, 3, 4, 5, 6, 7, 8 other pixels, isn't it? That's difficult to imagine that it happens on all of them at the same time with the same intensity if it's just random noise. However, if it's not random noise, if it is an actual peak, then you would expect that the central pixel would have the maximum intensity and the pixels surrounding it somewhat less intensity, even maybe 2 pixels away, even lower intensity, and so on and so forth, isn't it? So the minimum number of pixels that should be considered a peak is also a cutoff parameter that prevents noise from coming in. So the minimum number is 1, but maybe you can get away if your peaks are relatively large, you could get away with 2 or 3 pixels. You see that the minimum number of pixels in a peak would be that much. Okay, then log gradient. So log B K gradient is log background gradient, local background gradient. So how do you know what your noise is? How do you know that a signal is a signal? Well, you know that a signal is a signal because it is much bigger than the noise. How do you know that the signal is much bigger than the noise? By measuring the noise. And measuring the noise means measuring the background. So this is basically a donut-shaped region, okay, around what you tell it that the peak is, and it's a donut-shaped region that is defined as a circle without where the peak should be, and that's the region that we consider should have no other peaks, and it's the definition, and it's going to take the definition of the background from that region. Okay, so it could be 1 pixel, it could be 2 pixel, it could be 3 pixel, whatever. Okay.
So the number here 4
means 4 pixels.
Oh, you want to detect 4
exactly.
pixels around.
Exactly. 4 pixels minus 2.
Oh. Okay.
See? So then radius, these 3 parameters come from, they are for indexing, not so much for finding the spots, but for actual indexing. So the radius is, okay, so now we want to define a radius where we might find a pixel. Okay, so what's the size of, where we might find a peak. So here we have it defined as 3 pixels wide. So that means that in 6 pixels, it's going to try to find a single peak in an area defined by 6 pixels. Okay, and it's going to see if it can find the peak. Sorry, no, this is the integration radius. Sorry, not this is the integration radius. This is actually for integration, not for indexing. So this up here, the min-pix count, that is for indexing. So that is what it's going to tell you. Okay, this is the minimum size of a pixel, of a peak. Therefore, if this has at least this size, that's a peak. Please try to see if you can index your image based on that. Okay? Now, the radopt is actually for integration. So what this is telling you is that it's going to take an area, okay, that is at least 3 pixels in radius, or not at least, that it's exactly 3 pixels in radius, so that means 6 pixels in total, and it's going to integrate all of the values in all of those pixels, okay, to produce the value that you will find in your file. Remember, you will find in your file, you will have an HKL index, or a Miller index, say for example 048, okay, so H0, K8, L12, whatever, okay, and next to it you're going to have a value. That's your intensity, isn't it? How do you get the intensity? Well, the intensity you get like this. You take the region where you find your peak, okay, and calculate, so integrate the values, the electron count on there, and that is going to give you the actual value of that reflection, isn't it? Okay, so now how do you define what a reflection should be? Just like that, you tell it, okay, I want the reflection to be the integrated density 3 pixels around what we defined as a peak. Yeah? That's the rad opt. Rad mid, okay, in 5 pixels, say in this case it's 5 pixels, that's going to determine the noise surrounding that peak. Okay? Again, it's a donut shaped geometry that's going to be 5 minus 3, you see what I mean? And that's going to be, that means that it's a donut that is 2 pixels wide, and which has a hole which is 3 pixels, it's 6 pixels wide, the hole, isn't it? Yeah? And so that donut, it's going to take all the pixels in that donut, okay, and that's going to be the background. Yeah? And so that's how you're going to get a second column with the noise. Okay, So, okay, then finally you have rad up, up, okay, or max. Here it's called up for whatever the reason, but you have that one called max if you want. Okay, so what is the max value? Well, the max value is a larger radius, is 6 pixels wide, okay, and it will prevent other other peaks from being within that radius. If peak finding here found peaks that do not comply with the rad max, some of those peaks will get thrown out. Okay, why? Because if peaks are too close to each other, they may mess around with your estimation of the background noise, but also with indexing. Let's imagine that you have two peaks so close together that they fall within the rad opt value. Then what will happen with that? First of all, what will happen is that you will overestimate the intensity of your reflection by a factor of 2, isn't it? Because you will have 2 peaks instead of 1. But not only that, you will reduce your you will reduce your milli index by one step. You see, let's say they are all on the H line. Okay? Let's say that I can measure H1, because remember, they get closer and closer together, isn't it? As time goes on. So that means that, let's imagine that this is my point from 0 to 1. Okay? This is from 1 to 2. This is from 2 to 3. This is from 3 to 4. And now let's say that from 4 to 5, okay, then you cannot tell the difference anymore between them. Okay? What happens then? That 5 got the index 4. So that H equals 5 got the index H equals 4. And now your unit cell is not correct anymore. You see the point? That it's not only about the intensities being wrong, it's also that the Miller indexes will be wrong, and then your entire system falls apart. You see? Okay? So that's why it's very important to keep those correct. Okay? And then you have SAPI here. SAPI, it's, let me see, where is SAPI? Here, SAPI. It's sampling pitch. So you have here SAPLI and DECIT. Do you have DECIT somewhere here? You don't have it defined here, do you? No. Let's write it, because DECIT should also be in here. Okay. It's not, it's in more. Okay, let me just do it like this. Where did you get these files? Do you remember? So, here we should have DECIT. Equals, let's say 4 for the moment, okay? And we can save it. So now my suggestion to you, so no, like this. Okay, so my suggestion to you, okay, is that you go for the ones, you start your parameters based on the ones we got for MMCPD2. So because those are already optimized. Yeah? And so let me show you, okay? So the idea is the following. So if we go here and we look at all of them, okay? See, we have here opt1, okay? And so this is opt1, okay? Now if we go to opt2, see, you see the threshold is set up at 2000, and see now I am removing minpix count. Remember the what's it called? This thing here means commenting out. So I'm removing minpix count, and see now here 0 to 4, you see, where is it? Exactly, see here. This value is simply some value, and you see now for minpix count in sequence of thresh minus to thresh plus in steps of 1, then do all of this. You see? So that means that what's happening is that now it's going to run 4 runs, okay, with different min-pix values. You see? So then that's for 2, then
Do we
3.
need to add this it for second?
Yes, of course, because if not, so if we look at 3, okay, see in 3, you see now you have min-pix count of 2, so threshold of 2000, min-pix count of 2, log background opt of 4. So now we're doing log background opt, and so it goes from 0 to 8 in steps of 2, okay, and so it's going to run 4 runs, okay, in steps of 2 for for log background radius at value 0, 2, 4, 6, and 8. So 5 runs in total. Okay. So then you're gonna look at opt 4. Okay. And see in opt 4, it's removing minus NR. Okay. And so you see minus NR now is gonna run from 6 to 14. Okay. So sorry, I didn't explain minus NR. SNR is signal to noise ratio. So that means that a peak will only be accepted if it's at least this much stronger, 6 times stronger than the noise. Okay. So now my suggestion to you is that your initial values should be the ones that we obtained for the optimization of the what's it called, of MMCPD2. Why? Because those ones already worked really nicely for MMCPD2. There is no guarantee that they will be exactly the same as the ones for Crabtree. Okay, there may be some differences there. Okay, but they should be good enough that you should be able to work with them. Okay. So let's see, okay? So that means that to do that, of course, we should have so let me see, PWD, so let's do ls, should be in here, isn't it? Full procs, and then full procs, we should have MMCPD2, yeah, MMCPD2 is here, you see? MMCPD2, and let's take in here, and let's take any one of them, okay, and index all, again it doesn't matter which one, okay, and shift 1. So the only thing I'm doing here is, so more, so at the beginning of each stream file you have the exact command that was used to start the stream file. See, up here. See? So I mean, we can copy this, okay? And now we can bring it to opt sh, okay? And so what we do is, see, up here, I'm gonna copy it as a, and I'm gonna delete this one. Okay, there we are. Okay? So, and so see, now we have here all the values that we need. Okay, so let's see. Indexing Xcandal lat cell, Dirac lat cell. So is it like that? See, Dirac lat cell, Xcandal lat cell. Okay, we have it here. You see, in indexing, and here indexing Xcandal lat cell, Dirac lat cell, and here it's simply the opposite way around, but it doesn't matter. In both cases, we should get all the data the same way. Okay, peaks, peak finder 8. Integration radius 356. See, integration radius 356. That's rad opt mid, rad opt up. Yeah, 356. Okay. Then tolerance here 10 10 10 2 2 2. Okay. Then we have retry, multi, check peaks. See, retry, multi, check peaks. So, okay, good. Then, so then Mimpix, see, Mimpix count 1. So we set it here, Mimpix count 1. Okay, local background radius 4. Local background radius 4. X Gandalf sampling pitch, that's SAPI. Okay, 6. Okay, Desit is, where is it? Grad desk iteration 4. So there we have it up here.
Oh,
okay. And then we continue from here. So threshold 2000. So we started here at 2000. Okay.
2000?
Yeah. See, threshold
2000.
2800. Sorry, 2800. Min-SNR 5. Okay. Integration radius 356. That we have. Log background count we have
Yes.
4. So and everything is correct, isn't it? So the only thing we need to do now is disconnect threshold. You see? Okay.
Oh.
Okay. Oh, I see. This was the point. So, and then here we need to modify this to write thresh. That's why the threshold wasn't thresh, isn't it? That's the name of it, isn't it? Thresh. Yeah, exactly. And so observe we have 2800. Now we don't know how much it goes up or down. Okay, I recommend that you do a big test there. So, for example, what you could do, we always try to do 5 steps. So 1 in the middle, plus minus 5. So, for example, what you could do is, for example, from 2000 to 3600 in steps of 400.
Okay.
You see what I mean? So we do it in steps of 400. Okay, so thresh minus 2400, 2000. So 2000, okay, and then here we go 3200, 3600, okay. You see? So that is going to, and then here
How
we
many
set it in
runs
steps
will it-
of 400.
Oh, this is the
Yeah, that's the step.
step. Okay.
Okay,
Okay.
you see? So in that way we have steps. It's going to be 2000, 2400, 2800. 3200, 3600. Okay, so now we can save it. Okay, and the next thing is, so the other thing I want to check, okay, because I can't, so this one should work like this. Okay, and oh yeah, this one should work like this. So now the next thing before we start it, I need to check how to send it to so do you remember, how do you send the jobs? And when you're doing the detector distance optimization?
Since the job.
Yeah. How do you start the job? So
You mean
Default.
Python?
you run it with Python, yeah,
Yeah.
because you're using Emma's script. This is my older script because I couldn't be bothered with theirs. It didn't work and it needs something new. Okay, so then let me just check real quick. Okay, in what's the name of it? Yeah, what's up? Yeah. Okay, good. Then I'll send you. Okay, see you later. So let's see. Here and now we go MMCPD2. Let me just check. Let me just see which one is the oldest one. Hey. Okay. So okay, 31 to 32. So then nope, this is not it. Was it here perhaps? 23 to 25. Let's see. Oh, param. Yes. Okay, and yes, exactly. This is where we went. You see, we have 2,800 here.
Oh.
Okay, so what I want to check is how did I run this? Let me see. More. No. Opt. Message. Okay. And so this is like this. Was it with QSub? I think it was with QSub. History grab minus QSub. No. And let me see. Okay, let me just check real quick, and let me also see that this is correct. Okay, so that looks okay.